start. So we maybe there are some other students or professors will come. So let me first introduce Professor Lin. So it's a very great honor to have Professor Lin here. So I met with, so I began to read Professor Lin's paper 5 years ago. So the first paper that about complex fluid with Zhenlin. So it's 2015. So there is one derivation I could not derive it, and then I sent an email to Professor Lin, and then Professor Lin provided the detailed derivation to me. It's very nice. And then I met with Professor Lin in Nanjing, I think 2 years ago. So we have lunch together. So and yeah, we started this excellent collaboration with Professor Lin's PhD student Lingyue. So for Professor Lin, so he got his master bachelor in Nanjing University, and then moved to UBC to get a PhD. After PhD, he moved to Stanford to take the postdoc, and then got the assistant associate full professor in National University of Singapore that I was there. So, and then I think it's 2007. Yeah, Professor Lee moved to University of Dundee and became the chair, the professor and chair professor of numerical analysis. So Professor Lee has a lot of, I should say he's the top for the numerical analysis. It's well established, and also now he's working on some image analysis with some PDE basis, image analysis, and also some machine learning data-driven model like that. So now let us give time to Professor Lee.
Okay, thank you, Zhixin, for the introduction, and for the invitation as well for the talk. Also, Shixin is a good collaborator, so I'm very happy this the last 2 years we have done some works together. So this talk is going to be also a later part will be the collaboration of our collaboration with Shixin as well. So no, the title so in recent quite probably almost 10 years we also have been working on this phase field modeling and the computational methods, and so especially about 5 or 6 years ago, we developed a modeling idea for the phase field model. So this talk, I like to first introducing this modeling method that we used in the past 5-6 years and 5 years probably, and then recently we applied the method to the phase field, to the two-phase flow with moving contact lines, and then and especially application to the vesicle motion. And these are recent collaboration with Shixin, the work we have done recently. And then this, so the talk is going to be a collection of probably 3 papers, 3 or 4 papers with my former PhD student, Zhenlin Guo, and which Shixin also mentioned in the introduction. And then Lingyue Shen is current PhD student, and Shixin, and then Zhiliang and Huaxiong are, Zhiliang is from professor in University of Notre Dame, and Huaxiong is professor in York University in Canada. Okay, also Huaxiong is also a collaborator for a long time. Okay, so that's roughly the title and my collaborators. So let me roughly outline the talk for today. It will be, I like to introduce the method as I mentioned, which we call thermodynamically consistent phase field model for a two-phase flow, and especially it will be the incompressible two-phase flows. And then we will see how this idea applied to moving contact line, to the two-phase flow with moving contact lines. Then we will consider the application of this vesicle or a red blood cell motion in a narrowed channel. You can consider this narrow channel as a narrowed vessel, okay, blood vessel. Okay, and then we'll okay. The method we're going to use will be the continuous finite element method mainly. I will not mention finite difference method in this talk, and we are concerned with the two properties for the method. One is mass conservation, the other is energy law preservation. Okay, so then we will show some recent computations on this blood cell motions in a narrowed channel or vessel. Okay, so that's roughly the outline of the talk. And since I believe the audience are not not all in this area, so I will try to give a very basic introduction about the modeling method for this phase field model. So let me quickly mention. So the phase field model is it is about it's for the simulation computation of two-phase or multi-phase flows. So you consider have two type of flows, and then this the traditional method would be the sharp interface model, which is you consider fluid 1, fluid 2 are not mixed, right? And then the modeling is relatively easy for this kind of for if you do sharp, you consider it sharp interface models. That means you can fluid 1 you have well-known Navier-Stokes equations. You can model it using Navier-Stokes equation, and then kind of fluid 2. You use also Navier-Stokes equations. Then you can have it just you can easily write down the model for the sharp interface model. Okay, if we consider sharp interface for this two-phase flow, and then you only need it's just two different, say Navier-Stokes equations, but with different viscosity, for example, these two fluid, or and different density, right? So these are so you can easily write down the equations, and then at the interface, and then you can use consider velocities. For example, you can have this interface conditions. For example, velocity and force, right? You try to have some continuity along the interface. So then you can get the interface conditions. So these two equations could be put together. So the model is relatively easy, right? If you can develop these interface conditions, but computationally, usually then later, I mean the earlier stage of two-phase flow computation usually do sharp interface model, right? It's a modeling part easy, but computationally you have to write your own code, but usually difficult to have to use a general PDE computational code for PDE computational code to solve this problem, because usually PDE code you have to give a domain, right? Then you have the PDE written, and then you can apply it to solve. You have boundary conditions, and you can solve it. But now this case, sharp interface model, you have the interface conditions, and the interface between the two fluids are moving, right? Changing. So you have the interface conditions developed, and which is usually difficult to be incorporated into those general PDE solver, right? So then it becomes you have to basically try to write your own code to deal with these interface conditions. So it is that's why later, and there are certainly other reasons people start to develop a diffuse interface model, which is or consider this phase field method, or diffuse. It's called diffuse interface method. That means you allow the mixing of these two fluids, but in the very narrow areas near the interface. So you allow the solution to be smooth, change from fluid 1 to fluid 2 by introducing order parameter, which is we sometimes call the phase variable C, okay, which is C equal to, say, 1 or 0, stand for C equal to 1, stand for one fluid, and C equal to 0 stand for another fluid. And then you let C in this very narrow region, it's smoothly changed from 0 to 1. And then you get a continuous, so the solution is going to be continuous, but although you have a sharp change, a rapid change near the interface. Okay, that's called diffuse interface model, and they allow certain mixing in this narrow area around the interface. So which is you see the sharp interface model, then will have discontinuity, right, near at the interface. And we mentioned that there are computationally it is also harder to use the existing code. But then this one, you can see you get a standard PDE problem, and the interface can be catched by this variable C. So it will be level curve of the C at C equal to say, if C equal to 1 here and C equal to 0 here, then C equal to half will indicate the interface. So so this actual the order parameter, which in physics is called order, or this actual variable introduced and make the solution smooth, and then then you're solving a smooth problem, and then the interface you don't need to catch. In sharp interface model, you are catching the interface in the motion. You need to catch it, right? And here you can capture the interface by drawing the level curve of C. You can get the interface, but then everything you solved is a variable in the whole domain, and you don't need to worry about the interface conditions, right? Then you can apply standard PDE code to solve it. So that's so it's a typical this epsilon stand for thickness. You have a parameter which stands for thickness of this region, narrowed region. Okay, and then you can see the epsilon goes to 0. Then it is you expect, or it's desirable that when epsilon goes to 0, then your diffuse interface model or phase field model will approach a sharp interface model. Right? You get so that's roughly the idea of this phase field method for the two-phase flow. Okay, then they can apply ideas to multi-phase flow as well. So that's but now you can see the difficulty in the phase field in this phase field method is the modeling. Okay, first is the modeling, because which is it in the mixing in this mixed area, the mixing region, right? So how do you write down the model? And which is unlike here, you can use a Navier-Stokes equation with different parameters for each of fluid, but here you have a mixing region, so which will be make the modeling So we have benefits. You get the smooth solutions. You can have energy laws, right? And here it's very difficult to derive energy laws sometimes. But here everything's smooth, and then you have you have the you have energy law. Then you can for the PD, especially for the PD analysts, now we have energy law will give you some estimation of solutions, right? That's it will help you to do some analysis in PD as well. So there are many benefits of doing. That's why the phase field method or diffuse interface this approach becomes very very popular in recent years. Okay, so that's about roughly an introduction. So now I'm going to look at the modeling of the two-phase flow, and especially for the incompressible flow. So and now I'm not going to have two. Should I? Let me see. Should I have the?
I think
slideshow.
Slideshow. Yes. Yeah.
I should do the slideshow here. Okay, you go back. Yeah. So this let me. So okay, I'm not. I just try to give you some ideas, but it's hard to. There's no time to go into too much details. Okay, you basically have you can have a control volume, right? You can have you have two fluids. You can define in each different fluid. You can define mass, volume, right? Fluid 1, fluid 2, and then you can but you can have the volume which including both, right? And then you can define the density in each fluid. Okay, the density of single fluid, which you can define as mass divided by volume, right? And you can define the mix, the density of for the mixture regions, but also it will be the mass for the fluid 1. It will be mass 1 divided by the whole volume, right? Whole volume, which you can have the density for the mixture fluid, and then okay, then you can have this will be the density which we are really interested. Will be the mass, right? You consider of this control volume and divided by the whole volume. That's the density of the mixture, right? For the mass of the whole control volume divided by the volume, right? That's give you the and then you can also define volume fraction. So these are that means the ratio between the volume 1 and the whole volume, right? The whole, and then you can also find the mass fraction, which will be the mass of fluid 1 divided by the whole mass, which you use these quantities, right? C, gamma or C stand for this, and then this will have this kind of properties. But these are what I mentioned. These quantities and this law is certainly will be interested or we want to derive the equation for the law. Okay, and first, right? So you write down the equations. Basically, you want to have the you want to see the mass conservation, the equation first, and then you see the momentum equation that later we mentioned in which standard mechanical equations which you want to develop for this for these quantities. And now we mentioned earlier for the diffuse interface model or for the phase field model, you have phase variable, and then you can use either this gamma or this C as the phase variable. Okay, let's see this. So anyway, there are through some computations and then you can find. So what I want to find. So what I want to mention is you can find the relation of law, this density, the quantity you're interested, and then you can find this law. So you don't need to look at details of the computations, but you'll be able to find a law which can be written in this format. So this law 1, law 2 are density of each fluid. If you consider incompressible flow, and then you can assume rho 1, rho 2 are constant, right? Rho 1 is a density in the fluid 1, rho 2 is constant in fluid 2, because you consider incompressible flow. Usually it's almost constant, right? In fluid 1 and fluid 2, the density will be almost constant. But because you consider mixing regions, so the density will be not constant in the mixed region, which you can written as, so if you're going to use C1 as your phase variable, and then C2 will be equal to 1 minus C1, right? So which will give you the representation of density in terms of this phase variable C, okay? And you can easily see C will be equal to 1 if rho equal to rho 1 and C equal to 0, rho equal to rho 2, okay? You can if you from these representations, okay? So C equal to 1 and 0 will stand for different fluid. You can easily see because through the definition of C, so you can see the C equal to 1 would be the fluid 1 and C equal to 0 would be fluid 2. But you can see the C would be something like our phase variable we mentioned earlier, right? And then you have the relations. But if you consider this if you consider gamma as the phase variable, and then you can get expression of law in terms of gamma here, and this will be gamma, and this will be 1 minus gamma, right? So because gamma 1 plus gamma 2 equal to 1. So it will be you can use gamma as your phase variable. Okay, that will be the volume fraction. Gamma is volume fraction, and C is the mass fraction. We're going to use mass fraction as volume as our phase variable. Okay, C here. Oh, it's not going any further. Okay, and then oh, I missed the page here. Okay, here. So so then you can easily from mass density conservation, all right, for so the mass conservation, okay, so which will of fluid 1 and fluid 2, this will be the usual mass conservation equations, okay, for fluid 1 and fluid 2, which are standard equations. I'm not going to derive it, but people, if you go into the areas, you know this will be usual mass conservation equation, okay, for the because fluid 1, fluid 2, certainly you should have these equations. But then what we want to consider is for the mixture, the density, right? These are density of fluid 1 and density of fluid 2. But we are interested in this density of mixture. You also want these equations, right? This mass conservation for the mixture, the density law. You want these equations, and then you have to assume, make some assumptions. Okay, so if you assume this, the velocity, so your fluid 1 you have velocity v1, fluid 2 have velocity v2. But then what is velocity in the mixture area? Then you have if you define velocity in this called mass average velocity, and then you from these two equations plus this assumption of velocity, and then you get this mass conservation for this phase field model of the mixture of these two fluids in the mixture region. So then you can get a mass conservation equations which are very with these assumptions. Okay. And then you can see, then for the mixture, you get this divergence V, which will be equal to, based on these equations, you will get something like this, okay? And then you can see the divergence V with some computations. You don't need to worry how, and then you can get it's equal to this. And now, because C is equal to constant 1 and 0 in the bulk region, but in the interface, near the interface, C is not constant. So the derivative is not equal to 0, okay? So that means in the near the interface you don't have divergence free. So we call this, because usually for the incompressible flow, you have a constant density and then you have divergence free conditions. Usually you have divergence free equations. But now for this case, in the mix, in the near interface region, you don't have divergence free. In this narrowed interface region, you don't have divergence free. But in the other away from interface, you have divergence free. But so we call this is quasi-incompressibility conditions. Okay, and now you people. So these are based on the ideas which is done long time ago, which by Lowengrab and Trzasklinowski that time. It's famous paper for the phase field model. But people try to there are people try to get divergence free conditions because we are considered incompressible flow, and then you define the velocity in the mixture. They define this called the volume fraction. Okay, here we define this volume the velocity by mass average. But here, if you define as a volume average, and then you get divergence free. but this is not people usually used, but people do develop thermodynamic consistent model for this kind of volume average velocity, but it's not popular. And some works by Huang's group, and they showed seems to be this volume average performance seems not as good as mass average flow, or there's some unreasonable performance for the volume average flow. Anyway, it is more difficult to derive a thermodynamically consistent model if we use volume fraction average velocity. Okay, but anyway, so these are theoretically. So here we're going to use mass average, but certainly whether you should use volume average or mass average, there is certainly you still can try to use volume average, but which one is more correct? There are some papers that mass average one is better, but certainly all this has to be has to be checked by experiments, right? Which one is better? But certainly there's no such experiments at the moment for such study. Okay, so but we're going to use mass average. Then our equation would be the divergence not free near the interface. Okay, so which is called quasi-incompressibility conditions we're going to use. Okay, so let me just quickly mention the modeling idea. We don't have, probably I will spend too much time don't want to spend too much time here to provide too much detail here. But physical, so from your, so we can define so basically we can use some physical equations, right? Like mass conservation, we just had the mass conservation equations. Then we can use momentum. We can momentum energy laws, which will be able to derive other physical equations. So, but first you need to define physical quantities, which is the mass, momentum here, and total energy. And then if you consider temperature, then you can have you can define entropy, and this little s will be the entropy density. Okay, and now you need this mass of fluid one. Okay, so you can write the mass of fluid one as this, because we define C is a mass fraction in fluid one. Okay, so so you can define these physical quantities here, and if you consider energy temperature, then you have this little u here is internal energy, which associated with temperature. But we probably don't have time today to discuss this, because later our model we're going to discuss applications in the blood flow in blood vessel. So we are not going to consider temperature there. Okay. But the framework of the modeling idea is applying to the thermodynamic with the problem with temperature as well. So this quantity defined, and then this is about the internal energy. I'm not going to discuss it. And then, but you can basically write down the formula for internal energy, and then you can get expression for the energy as well. So now here is a balanced laws from mechanics or physics. So you have mass conservation, which we already have the equation, right? And then you have momentum conservation or Newton's second law, which you can, if you go back to check your university physics modules, you take this university physics course, you will see this kind of equations for the momentum conservation, right? This change of momentum, which will be can be written in this will be m will be the usually stress, the force, right? Which is it's kind of the momentum flux or something like. So this will be and this will be the body force. Or it is gravity, right? Gravity force. And then the and then you have energy change, which is written usually it will be equal to the work you did, okay. And also if you consider temperature, then you have heat, okay, part. But these are this will be called the heat flux, and this will be the classical. First, it will be the classical kind. You can think of this energy flux, but it is work. Okay, the integral will be the integral will be called work. Right? That's and then you can have entropy, which is classical, and this will be the entropic flux. Classical entropy flux is defined by the classical this heat flux. Okay. So this QE is called the classical physical. There's a classical heat flux which is proportional to gradient of temperature. Okay, these are standard. These are standard. These are all standard terms. So for us, all these terms are written here are standard. You can find from university physics books. Okay, which is a standard term. But this, because we are interested in phase field model, which have the mixing regions. How do you? Then because of that, we have to introduce some non-classical terms, which we don't know, right? So we put here is another heat flux which associated with the mixing region. Which we call non-classical term, which we need to determine later. Okay, these things we don't know. It's a new thing, and these are classical one, which you can find from standard book. Okay, and also for the entropy change. Okay, the change of the entropy, which will be or the rate of change of entropy, would be the classical entropy flux, which is defined by the classical heat flux divided by temperature. Okay, these are with, but I'm not going to spend too much time about it. But then you have also, because of this mixing region, which you don't know what it's going to be, it's non-classical term. So we define as a non-classical entropy flux, which we're going to determine. We need to determine later. Okay, and then you have the second law of the thermodynamics, which you have entropy generation term, which has to be non-negative. Okay, that's the second law of thermodynamics, which the entropy generation has to be non-negative. And then we have another for the fluid one, the change, the mass change for the fluid one. You probably will see because of the conservation of mass. So you see the conservation of whole mass is 0, but the conservation of the fluid one mass, it is supposed to be 0 as well. But now you have this mass flux here, QC. But why it's not equal to 0 is because it will be the mass conservation. If you look at the previous mass conservation of fluid 1 equations we have here, so this will be the mass conservation for fluid 1. And now you see the velocity is V1. Okay, you get 0. Okay, that is supposed to be 0 if it's V1. But now since our velocity is not V1, it's a mixed, it's V, right? Now velocity is V. So this the mass conservation equation will be so it will not become so the change of mass will not be 0 here for fluid 1 if the fluid go with the V, right? It's not going to velocity V1, but because it's not so this this DC, this derivative it's called the material derivative. It's basically 2 terms we mentioned it earlier for the mass conservation. You have 2 terms, which basically for the derivative, this derivative will give you 2 terms, which we see earlier. Okay, anyway, so these are balance laws of the system. So how do you derive the equations? Then you can just you work out all, because you know these quantities, right? You just finish, you write just work out these derivatives here, because you know the quantities we defined in the previous page. And then you just work out all these expressions, and then eventually you can get the expression for the S generation, the entropy generation term. And then because entropy generation has to be non-negative, then you can determine, then which limited the choice of your QE and QS here. But then you can find the expression for this for these non-classical terms, and then you can eventually get. These are classical terms. We mentioned this classical heat flux, which defined by the gradient. It proportional to gradient of temperature. Okay, but the non-classical one you have, because you want the entropy generation term to be non-negative, which will give you the expression for the non-classical terms. Okay, and then you can get the expression for the QC. This QC is also unknown flux, which you can determine through this. You want this as generation term. It has to be non-negative for all the choice of these quantities, then which will give you the relations which here. And then this stress, this M, and which are classical. Okay, these are all classical terms which you can have the definition here. Okay, and these are come from you can get, and but other will be non-classical, which you can determine through the. You have to have this entropy generation non-negative for all possible choice. Always has to be non-negative, which give you the you can determine. But we can show this later. Okay, we can give you examples later when we do the moving contact line model. You can see this how we choose these terms. But here I just write down the term, and then you can get the model. This term. But there's coefficient that you have some you have some choice, okay, different choice of this mode, which you can choose one which to satisfy, say, Ansaga's reciprocal relations, or you can make it is Zhiliang invariance. That means the coordinates unchanged. The model is not changed with coordinate change, right? And this people are talking about Ansaga's law. Now based on generalized Ansaga's law and so on. So you can choose this term satisfy Ansaga's law and so on. So this will be kind of our modeling idea, which we think is more general than Ansaga's law, because you can have more choice here to make it satisfy Ansaga's law. If you can also make it not okay, and then you can get the model. Okay, I probably wouldn't or don't want to spend too much time. And then here. You can this coefficient or then you have the choice. You have a choice of the internal energy, or the different energies. I mean internal energy, or the if it's no temperature, then you have to choose this Cahn-Hilliard, this standard for the double well energy and so on. So you can have a coefficient lambda t, which if it's dependent on temperature, then usually we assume the linear dependence of temperature. Then you can have this coefficient, which will be for this standard phase field, free energy, the phase field free energy, which is called Cahn-Hilliard, this free energy. Then you have a coefficient which may linearly depend on temperature T here, and then you can have this lambda s. These are the coefficient of the temperature. Okay, this lambda t is written as lambda st plus some other constant lambda mu. Okay, it is written lambda st as lambda u plus lambda s times t, basically written. So anyway. There's a lot of details I'm going to skip here, but we'll see, because this is general modeling idea I just quickly mentioned. And then you can actually get this expression of lambda t by these are energy law, this thermodynamics. We call the model is dynamically consistent, right? That means that this energy law, or some first law of thermodynamics, or second law of thermodynamics, which is entropy law, are satisfied with the model. And then you can do this limit. Like we mentioned, if you let the thickness of the phase field, the interface region goes to 0, then you can derive you can approach the sharp interface model. You assume it's approach sharp interface model, then you assume the surface tension of sharp interface model, which is linearly dependent on t, and then you can actually determine this coefficient lambda t. Okay, by doing this limit, and then you can actually derive this interface conditions here, which you can compare with sharp interface model. People derive the interface condition before. Okay. But you can take the limit, you can reach the sharp interface these conditions. You can see, you can compare with the existing one. But this energy is very rare. You can see because we are considered temperature as well, and then this interface conditions people you never see in the literature. But we derive this through the limit of sharp interface model. From feasible to the sharp interface model, you can derive this condition. You can also get we mentioned this coefficient for the free energy lambda t, which is through this limit. You can get the surface tension limit is given by this. If lambda t, so this is lambda t. Okay, so then if you write lambda t as eta sigma, and you basically this will be lambda t times this. If you want this to be equal to sigma, which is the sharp interface surface tension, and this is surface tension of the phase field model, the limit of surface tension. If you let them same, then you have to choose lambda t equal to a constant times sigma of t, and this constant will be equal to 1 over this number. Okay, and then this will be the theta will be the coordinate vertical to this interface. Okay. Anyway, but these are things you can derive through the model, and then through the limit of the interface width goes to 0. Okay, but now I just quickly like to mention, now we can use the idea for the phase field model for the moving contact line. And these are a collaboration we did last year with Shixin is one of the collaborators for this. And then we have the students, Zhenlin Guo and okay. So now if you use a similar idea, and you can define same quantities here as we did before, but now we don't have temperature. But our energy, okay, so didn't mention this free energy, which before we didn't write down this free energy, which is this double well energy, which is written here. And these are called Ginsburg-Landau or Cahn-Hilliard free energy, okay, which is a standard in the phase field model. And now we have this extra energy, which is for the moving contact line, which is taken from the from the literatures, which is especially this three famous the paper by this famous paper by researchers in Hong Kong, the University of Science Technology in Hong Kong, which is Tiezhen Chen, Xiaoping Wang, and Shen Ping, Wang Xiaoping, Qian Tiezhen, Shen Ping. They have the they write down this they write down this energy which for the interface. So if the moving contact line means interface of your fluid interacting with the solid boundary lines, and then this interface is moving along the solid line. So then the interface, how this interface interacting with the solid boundary line is moving. It has to be a slip boundary, along the boundaries, along solid boundaries. This interface also slipping, is moving. So and which give you energy, which is written in the, we taken from there. So the quantity are similar, but except that you have extra this interface interacting with boundary energy, which is written here. Okay, other quantity are similar. Okay, and now you can write down then you can write down this balance law as we had before. Okay, so now we just change the notations a little bit, but it's same as before. Now we don't have gravity written, but you can also add gravity here, no problem. And then you have a part, so this stress term just same as before. Okay, so but still, it basically in this paper we write this m into including two terms, but one is classical, the other is stress for the interface. Okay, so anyway, but these are just same as before. Okay, and then you have now you have this time there's no entropy, but you have energy dissipations. Okay, so now the change of energy, let's written as delta. And now this equation is same as before. And then this one, so now we have this energy, we assume, because if you don't have internal, external force, okay, let's assume everything, there's no extra external force, then this energy change has to be, the energy has to be dissipated, right? So that means that the dE dt has to be negative. So that means this term delta, which just like entropy generation term before, has to be non-negative. Okay, so then we can get same as before. We just do derivative of all these terms, then we can get expression for this delta, capital delta. So we can get expression for delta. Then we want, no matter what change you have, you want this delta has to be non-negative. Okay, so then you can derive the model. And then here the boundary conditions, we just mentioned this general Navier boundary condition, which for the moving contact line, then we assume the tangent, its normal is equal to 0 as a velocity, and tangent velocity equal to u tau. Okay, this is slipping, a little bit slipping, but this has to be determined through the modeling we just had before. But these are format of boundary condition we taken from this three people's paper. And then also the C, the boundary condition for C, they also use the Allen-Cahn type of boundary condition, which also in this format. And then this gamma is a interface, okay. And then this will, the gamma is a boundary, right? And then this also need to determine. Okay, you also need to determine this J gamma, which in the form. Then you just you differentiate, you do the derivative for all these terms here, right? You have the energy expression we had before. You have all these terms you had. So you just differentiate all this, and eventually you can get. So do the differentiations, then eventually you get a d dt. Okay, you can write down dt, which is we define as negative delta, right? Negative delta. So these are all the part is negative delta term. So you want, no matter what this variable going to be, you want to negative delta to be, you want the delta to be non-negative, right? So you can see here, so because this sigma c is a stress, okay, which you need to determine, and sigma eta is standard stress. I mean classical stress, which will have the formula, and then sigma c is thing you want to determine, which you want this to be non-negative, because this c is, you see this term is depend on c, and this is just the stress you want to determine. So if you want this, no matter what c changes here, you want this to be non-negative, then you have to choose this sigma c equal to negative that to make it 0. Otherwise, it's not possible to be non-negative, right? Because these are different variables here. So you have, that's give you the choice of sigma c, right? Similarly, you do a choice of other unknown terms, variables. You can do this kind of change to make it non-negative, right? All the terms have to be non-negative, and then you can determine those terms you don't know, or non-classical terms you can determine. Okay, and then eventually you can see here the sigma c equal to negative this, right? That's exactly we want how we make the choice. And I can derive this moving contact line models. Okay, I can write down the model here. So these are I try to give this a general introduction of this. How do we do the modeling? So now we can just go back to the last part of the talk. We can see is that time. Oh, it's almost. So let me. So Shixin, I have 1 hour or the talk.
I think you still have like we can extend it to another 20 minutes.
Okay, 20 minutes.
Yeah.
Oh,
20 minutes or 50 minutes. Yeah.
Okay. I probably just need 10 minutes. 5
okay.
or 10 minutes.
Okay.
Probably need 10 minutes. Okay. Let's see. So now we're going to consider this the applications which we work recently with Shixin, also a collaborator. So we consider this vesicle motion, but we can particularly, if you consider you can consider this red blood cell as kind of a vesicle, and then you usually these are biological you usually have a membrane. Okay, it has a biological membrane, and so it is can be so the vesicle can be considered as two-phase flows, but we don't need to. I'm also not I'm not expert, but in the real applications, but just you can consider the vesicle as two-phase, okay, two-phase flows, and then the so basically the model you have. So the vesicle will be you have the surface conservation, and then you have mass conservation, and these are so the surface. If you consider the density the same, then surface conservation will give you. So that means that it is not so the surface is not extensible. Okay, you have the extensibility. So so you have inextensibility of this vesicle. Okay, and then certainly you have mass conservation as well for these vesicles. Okay, so we just quickly mention some literatures. So we consider vesicle as this another phase of fluid, right? It just like we consider phase flow, this two-phase flow as we did before. So and then there are many different methods. Sharp interface method for the vesicle motion. Okay, and then you have phase field models developed for the vesicle motion as well. So I just list some here, but what we are interested is how this vesicle or the red blood vessel passing this narrowed blood vessel. Okay, the red blood cell passing red blood vessel. So so that means it will contact this this vesicle will have contact with the boundary. Okay, so that's why what we are interested. So there are many works before, but there's no such work available before. Is to consider this vesicle or this red blood cell has contact with the boundary. Okay, so then if you have a cell passing this narrowed blood vessel, then it will contact the boundary of the vessel. Okay, and then it will be the moving contact line problems. So that's why we are that's why we need to derive rewrite the model, and then we'll see the simulations. Okay, so basically these are so now we have the ideas of how we derive model, right? We can now, because for the vesicle, usually people so you have a kinetic energy term, which we same as before. Okay, we wrote before the energy, total energy. Which it's important in your in the previous derivation of the models, but now the total energy is a little bit different from we had for the fluid model before, and now you have something called but these are taken from previous work, for example by this Changdu, Chen Liu, and Wang Huaxiong. Okay, for example, they have this kind of energy written before. So it will be the kinetic energy, and then you have the cell, the binding, this energy of this E cell stands for the binding energy. There is expression here, okay, and then this what is F and so on. So I don't have, but these you can find from literature, okay, and then these are binding energy. I'm not going to explain it here, but you have this thing which is volume, this volume conservation. That because here we consider density is constant at the moment, so then the volume conservation means mass conservation here. Okay, so this energy, this will be it's kind of, you can think of this as a penalty. So you want this volume to be conserved. Okay, here. So then if mv time, so this is like the in the energy term, you adding this means you have a in the optimization, right? You have a penalty which to try to enforce this volume to be conserved, and then you have surface area. We mentioned in extensibility, which will give you the surface area to be conserved as well. So you want to force this surface area to be converted. So there's another penalty term for the surface area, okay, and then which will give you this energy, the second term of energy, and then you have the moving contact line, this energy we had before, okay, because we are going to consider moving contact line, because these are we are particularly interested in this work. We want to see the so then you can basically do the same. Now you have the expression energy, then you can see as we did before, you want the change of energy which is equal to negative delta, right? You want delta to be non-negative, then you can basically derive these models, which is written here. I'm not going to mention this in detail, but you just need to work out all the terms, and then you can have the you can get those terms, specific terms which you need to determine for this model. You have a few terms which you are undetermined. Then through the which is non-negative, this delta to be, you get the expression for the delta, and then you want delta to be non-negative, which will get you basically you can get the equation. You can get these terms. Okay, you get these terms in the general moving. This for the moving contact line, you have moving contact. This J gamma and U tau are this associated with the moving contact line boundary condition, and then you have other terms. Now we have changed a little bit of notation, but it's basically it will be the other unknown terms in those energy and momentum law, balance law. Okay. Eventually, you can get this equation, which is written here. Then we have this extra condition, which is for which I'm going to explain later. Okay, if we have time, and then we derive the. So then you can have the or you do non-dimensionalizations, which give you this physical quantities associated with this model. Okay, but this will be the equation where I try to solve. So equation D is the extra, which we'll see if we have time. We'll mention that later. But A, B, C are we derived from the standard way, and then you can so then you can derive this energy law associated with, you have balance laws we had before, right? You can get energy law, and then we now we have a mass conservation, we have energy law here, so we want to derive, develop or we have designed a numerical method which be able to maintain the mass conservation and maintain this energy law, which we've written here. So we're going to use midpoint scheme in time, and we're going to use finite element method, the continuous finite element method in space, and then we can derive, it's called modified midpoint scheme, and with the finite element method for the spatial variable for the spatial discretizations, and then you can basically we can derive numerically. We can derive this energy mass conservation and energy law with I'm not going to. So basically, we can derive this energy law, okay, numerically, which is this expression here. Very similar to the energy law which we have here. Okay, and then this d dt, the energy dt will be replaced by difference. So difference is n time step n plus 1 divided by delta t. Okay. So but anyway, so these are, we can derive the method have this maintain these two properties. Let me just quickly show the computations. So we consider we just some verifications of examples. You can see it is if you consider this you bend this vesicle and then you let it, then you bend it, then you free it. So there's no, so the energy going to be dissipated. You see the energy, you can see our energy dissipation here, and you see the mass conservation here, and the surface and mass area conservation of this model. So basically, that's the motion of this vesicle. You see that there's no external force acting on it. So you see the energy, which is dissipation and the mass conservation in this. Okay. And now we have this two test examples, which are very also is existing in literature, which in this case, there is people have, so you have that, it's called tank treading and tumbling, okay. And now you can see the, so this will be, you see that it looks like this vesicle is stopped, but actually the surface is still moving. It's called the tank treading here. Okay, so and these are we all compare with existing here for the tumbling. You see it's tumbling at the same time. You see this surface are moving, and you have tumbling at the same time. And these are angles, which is of this certain angle, which is measured by, it's called the Jeffrey orbit. Okay, there's exact formula for the angle of this motion with the tumbling, the axis of this of this. So anyway, but you see the compare with this formula, which numerical and exact solutions which you get here. These are quite consistent to the theoretical values, which is called in this Jeffrey orbit example. Okay, so these are some test example of our method. Okay, now I'll just show. I guess the time is almost there. Let me just show that that's why I'm interested with this narrow gate passing. Okay. And with this, you see that it will touch with, I didn't mention the ratio here. I should mention before. First, for the case, it is not, for this case, for certain ratio of this, it's called, you see the height, you see this width and this ratio of this, okay, we're going to mention that for this case, it's not going, it's not passing if you with inextensibility condition, which is in. But if you don't have inextensibility, and then you see it will be passing it. Okay, so this inextensibility, which is I don't have time, which we have a local so we have to add this. There's which is called the local inextensibility in the literature, which there's actual equations. I just which I tried to I didn't mention earlier, or just mentioned, but we didn't explain it. So it is called the local inextensibility condition, which is given in the developed by this group, Zhenlin Guo and other people developed this, and you can see this important in the in simulate this motion. Okay, if you don't have the local inextensibility, then you see it can always passing. Okay, the change and shapes because the volume will be the surface will be extended, and then you can always get pass to the narrow, which is not realistic. So, but that is important. But recently, our test shows that it is not necessary to have this local inextensibility equation as well, because we have the term, of local inextensibility term, which is surface area, maintain surface area as a constant in the equation. We have that term. As long as your penalty parameter choose large enough, you can still maintain this inextensibility. We recently have this test done, which is so this local inextensibility actual conditions, actual equations we don't really need, because so that's why I didn't emphasize it in this talk, but we do mention that equation which in the other literature existing in this area. Okay. And now, okay, yeah, that is showing the right hand side, showing this in the second example, which is you see that it's not going to keep constant the surface area. Okay, so then you just some more tests for different ratio. It's called the surface volume, and for 2D, it will be just the length, and for the paradynamics, right? The what is called, but that's just the length of the surface or this curve, right? This closed curve versus the volume or the area of this ellipse. Okay, and then you see different ratios which will affect the changing here, and in this case, in this ratio it will go through, but in this case it will stop. Okay, so you see the ratio of the surface volume ratio is very important to pass this pass the channel. Okay, and then these are also the so mechanical property of the bending modulus, which we didn't emphasize, but that's the coefficient of that bending energy term, okay, which you can see it has different values, and it will also affect the passing as well. Okay, it will in this case it can for a fixed volume surface area volume ratio it pass, and then the other case, okay, sorry, it is pass, but it's different. You see the way of passing may be different if the bending energy is different. Okay, okay, I guess I need to stop here. It's too much. It's okay. What happens?
Okay.
Yeah, I think Shixin, so it's probably the time already. Yeah, I will stop here.
Okay.
For any possible question. Yeah.
Yeah. Thank you so much. So any question from audience, professors and students?
I actually have a very naive question about this scenario. For instance, well, I think you mentioned that for the there are some works that for this kind of system you can couple with the shear flow if it is on some kind of channel. Is that possible in your model?
Yeah. Yeah, it's from a model. Yeah, it is possible. So then your boundary will be moving with some velocity, right? Yeah. Yeah, the model certainly, we don't have example here, but we have other examples in other papers about shear flow. Yeah.
Oh, we have that. We have that.
We have that. Which one?
For the tumbling and tuck trading. Yeah.
Oh yeah, that one is shear flow. Right. That because yeah, it's moving. So its tumbling is come from the shear. Right. Yeah.
Yeah. Yeah. Okay. So which means different kind of shear flow will. I mean, not different kind of shear flow, but different kind of the magnitude of the shear flow will change this kind of passing phenomena, right? Yes. Okay.
In the shear flow case, yes, it will. Yeah, but we didn't for this passing case. We didn't try it because this in your blood vessel usually it's hard to make shear, right? You have to have the wall, the vessel wall. Usually it's not going to move tangentially. But anyway, yeah, what's the question then? Yeah.
Well, this question is quite naive. The thing is, well, what happens if you have some closed domain, not the channel, and in this kind of domain, and you have some, for instance, no sleep boundary conditions or this kind of boundary conditions, and then you try to put this kind of cells on it, and you try to use the cellular flow to flow this kind of blood cell or whatever. Is that possible to study this kind of model?
Yeah, it's certainly. I don't see any the difficult. So we write the model can include in this case, and then numerically, I don't see any extra difficulty. Yeah, but we just didn't try this. Yeah.
But in that case, this kind of cells could somehow rotate by itself, right? There might be some kind of rotating. So is that still fine for this kind of thing?
Yeah, just to mention our earlier case. This is this case is shear flow case. Just Shixin just indicating. So these are shear flow cases. You see the motion is rotating, right? This tumbling.
Yes, this one is
tumbling, and also it's not just tumbling. This surface is actually also rotating. You see, so this point is not a particle. It's just showing. Is this point just showing the surface is also moving? Okay, so that it's called a tank treading, but it's just showing the surface is also move. It's not just the whole thing is also tumbling. Yeah, this you can see this kind of thing. Yeah, the model can do this, no problem. Yeah.
So this kind of cells can both move and rotate. They can
Yes.
it can do it both. Okay.
Yeah.
I see.
Yeah.
They said, additional thing is, well, then is that possible? Then we put more than one cells on this.
That's I didn't. We're going to that's the future work. Yeah, we're going to put them. Now we just study one. We certainly like to do more. Okay, let me see. Well, we mentioned this in the other type of.
Yeah. So Lingyue has did several.
I didn't mention.
Lingyue has did several cell interaction.
Well,
we did that.
So you already is doing. Lingyue is already doing that now, or.
Yeah. Lingyue has do that test. So we mimic two cells passing through the natural channel at the same time. So there are some interaction between cell and the interaction with fluid.
Yeah, I should mention this future work. Okay, so already done this. So Lingyue hasn't told me that. Okay, so
did that.
Yeah. But we do want to see a large number of but even more than two, right? We like to do this kind of.
In this kind of
simulation, the computation maybe more involved because you have more this in any case there's all this cell this interface inside of the domain. The interface which is the solution is changing, although it's smooth, but it still changes quite rapidly. So you have many of these you have more of these things. It will make the simulation harder. And then
what kind of Thank you very much. It's very interesting. Yeah. Then in what kind of what should be the correct boundary condition for if you have more than one cells in this situation?
Yes. So the if you mean if the cell interact, if two cells. This has to be there was a that's interesting. It is let me see. So now we can have the these are particularly good for the surface for the phase field model.
Yeah.
For this case, phase field model, which is if you have two cells, if you have now we have two phases, right? If you have more cells, then you have more phases. Because each cell we assume may be different fluid, but you need to introduce for each cell, you need to introduce a different this phase variable. If you have two phase variable. If you now we use one phase variable, you have 0, 1 stand for two different fluid, right? So now if you have another cell, now then you have if you have other 3 cells plus original fluid, then you have 4 phases. Then you can use 2 phase variable, which stand for these 4 phases. So you can have C1, C2, and C1 equal to 0, C2 equal to 0 stand for 1 phase, and C2. So phase field then it's naturally for phase field model to simulate this case with this more, including more phase variables. Okay, but then certainly it will increase your computation cost. Okay.
Yes.
And the boundary condition, you don't need to worry. The good thing is that you don't need to worry about it. You just keep tracking this C1, C2, these variables. Then you just draw this level curve. It will give you what the shape looks like.
Yeah. So you just add extra repulsion energy between these different functions. Then
right. You can also add energies if you want, but if you want to see if you have the repulsion, if you have certain this kind of energy. Yeah. But if you want them to do naturally, then but anyway, they can be done. Okay.
Yeah.
Hi, Ping. Just say hello to you.
Oh, okay. Okay.
I was teaching, so I missed the beginning for all this talks. It's a little wonderful subject. So maybe I also ask slightly some simple questions, try to get the sense of what it's about. So I'm missing most of your talk since like the most computation. So this is a very typical problem. You have bending energy, you have a constrained surface area and constrained volume area, and so the most computational is able to do it is probably all on fast field, right? So if without the fast field sharp interface constraint is probably extremely difficult to do, right? So that was
so say that again. Without phase field.
So now I understand. So you're doing the phase field penalized, so you can make this formulate in a nice way, and it constrain like a surface, the total length, the surface area, total the volume, and you have the bending energy. So you have the really nice workable framework for the for the phase field and both. So my question is that if without use phase field is sharp interface or hard constraint, it's almost impossible, right? Or but is there any theoretical way people? So let me ask maybe simple as possible without flow, just Wehrmer flow. Wehrmer flow, the heat dynamic, the one. And suppose without usually, my question is that if we constrain on surface area and also the volume area, is this a very possible problem? Is possible?
It depends on, okay, let's see, So usually sharp interface model, it's hard to develop through the energy, right? Like
Wehrmer flow itself, we can do that. So my question, so if Wehrmer flow itself, we can define.
So Wehrmer flow can be done by energy minimization.
Yeah, that's right. Because
then you just simply add this, penalty.
Oh, I said, my question is that without the penalty, hard constraint.
Hard constraint.
Is very possible dynamic or not? Because eventually same question. If the
but hard constraint, you can do Lagrange, right?
Yeah, anything that so with the Lagrange, so basically you tell me this guy, if you doing the Wehrmer flow with constraint of volume and surface, it's a very possible mass question, right? That is basically my question. Do you know anybody work along this line?
I don't know. I think we did a phase field. I had a paper before with Shixin. We compare. So basically, now if you don't do penalty,
yes,
you do Lagrange formulation, right? And we have a comparison for the liquid crystal, right? For the liquid crystal model, we did a comparison.
Yeah.
I think penalty doing better.
No, that agree.
On our paper.
No, I definitely agree. Penalty is the penalty, and phase field is for computational is best. So there's no question about. My question is if any theoretical question people are studying this kind of. I know people studying Wehrmer flow is for a short time. You may can do. It's a very typical problem, but still interesting. But then if you add I guess for biology cell, the constraint on the surface area and volume is very important, right? That was I hear many people say that for cell you have to have a constraint on the inextensive the surface area and volume is important question in the cell biology that required this constraint or not?
Okay, so I'm not in the area, but I can see from here. It is important, the surface area. Otherwise, you always if you don't have surface area conserved, it always goes through the cell.
I see.
It always goes through, no matter how narrow it is. So it's just extended, right? The area.
Yeah.
No, it's just to go extended, then it goes through. So you can see it's so important that you have the inextensibility. Well, that means the surface area has to be maintained. And the volume certainly is mass conservation, right? They have to have mass conservation. The volume,
because incompressibility. I see.
Right.
So this are hard constraint. So it's an important question. So basically tell me for the studying cell dynamic, and Wellman flow coupled with conservation mass and volume and surfaces are important.
Yeah. So from physics, right? But mathematics, mathematically, they don't care really, right?
No, they care.
Yeah.
And I always just the important physics question more important. Yeah, I see. Okay, so you don't know anybody was studying along this constraint.
I don't know. Because we just entered this, but Shixin maybe know better. Shixin may know more because he did also before with Zhiliang, Zhiliang. They have some work on this. We just naturally extended to this just go. So I'm, just flow the ideas to this problem, specific problem, recently.
Okay.
Yeah.
Yeah. Really nice. It's really important and hard problem. Yeah.
Theoretically, if you want to do some analysis, probably harder, I guess.
Yeah, it's much harder. It's harder. Yeah. It's certain, definitely. Yeah. Thank you.
No problem.
Nice to see you. Yeah, nice to see you.
Nice to see you. Yeah, nice to see you. A long time. Okay. Yeah.
Quite some years, right? Yeah.
Yeah, quite some years. Yeah. So all is fine.
No, too fine.
Yeah. I saw the Huang moved to Duke as well. Huang.
Yeah, Huang. Yes.
Okay.
Yes. Yeah.
Just recently, or?
Yeah, just this semester. Yeah.
Oh.
Yeah.
Okay. So it's good to have this discussion, and thank you for Professor Li's talk. So if there's no question, so we finish our today's distinguished lecture. So so this lecture will also be uploaded to our center. So if you or your friends want to revisit this talk, you can go to our Zhongzhi Mathematical Center to find this record. Okay, so